All right, so you've got it here. You got a diagram showing 100 students from a previous section. The diagram represents the number of students who study art and biology. So A is art, B is biology. Okay, if we know that a particular student studies biology, how does that affect the probability that they also study art? Will you stop talking? If you know somebody already studies, let's do it this way. What's the probability that a student studies art? Looking at this. Studies art. What's that probability? Yeah, 36 out of 100. Okay, so the probability of A happening would be 36 out of 100. Okay, what about the probability of only A? Yeah, 24 out of 100. So only A, we'd write A intersect, not B. That's only A. That's 24 out of 100. Okay, what's the probability of studying biology? Okay, that's 40 out of 100. Okay, and then the probability of studying only biology, 28 out of 100. Okay, all right, so this would be B intersect, not A, 28 out of 100. All right, now, what you're figuring out next is what this question's asking. How does, if we know that a particular student already studies biology, okay, how does that affect the probability that they study art? So when you have you're right now, what you're doing is you're limiting what your sample space is. You're only going to look at students that study biology. Okay, because they have to study biology. So that means instead of looking at all 100 students, you're only looking at these 40. So instead of the sample space having 100 kids in it, it now only has 40 kids. And out of those 40 kids, how many of them study art? According to that diagram. How many? 12. Yeah, 12 out of 40. So if you're already part of this group, that's 40 students that we're looking at. 12 of those 40 students do art. So this is the probability of A given B. This would be, you studied biology. Out of that, what's the probability that you study art? That's going to be these guys right here. 12 out of 40. So the question's asking, how does it affect the probability that they also study art? Well, the answer is it's going to shrink the sample space. This is going to shrink the sample space from 100 students to 40 students. That's what this does right here. Let me just write it right like that. Okay? Given B, this is better. Given B shrinks the sample space from 100 students to 40 students. Okay, now what if I wrote it like this? PB/A. Okay, so this one would be studies biology given they study art. Okay, so studying biology, we did it up here, it was 40 out of 100. But now you're restricting it to only kids that first study art. So what that would do, instead of the sample space being 100 now, the sample space is only going to be 36. And out of those 36, 12 study biology. That's what this probability would be. Okay? So this shrinks the sample space from 100 students to 36 students.
You're going to specify names. Not really like such standard. So shots in this game, we have the rings.
Okay, so we got to find that shot. Great. All right. So that is that's what this does. Okay, so let's look at it as an example here. It says how many students study biology? So the number of students that study biology, that's with the little n on it. It's number of students, biology. Okay, we already said that was 40, and that's represented by this area on your diagram. Okay. Of those students who study biology, so now you ignore the in the rest of the diagram. You're only looking at that little circle. Okay? Of the students who study biology, how many study art? Where is this region in the Venn diagram? So now you're looking at biology only, and then within that biology only, or not biology only, but just bio, this little piece are the kids that study art who already study biology. So this region, we're used to it, we say it's the intersection of the two. The thing that makes it different is it's not the intersection out of 100 kids, it's the intersection out of 40 kids. Okay? So this is the notation to represent that region. And that's 12. And it's also, this is also the same as the number of kids that do art and biology. So given that they're a biology student, this is also the number of students that do art. Okay. All right, what's the probability that a student studies art given they study biology? Okay, so that is this, P, study art given biology. Okay, so this is your 40 students. And out of those 40 students, there's 12 that study art. Okay, so that's going to be, what, 6 out of 20, 3 out of 10. And there's your probability. That's the probability of this area right here. It's not 12 out of 100 anymore. This is where the denominator shrunk from 100 to 40. Okay, you got that? Okay, now we're going to write out what these rules are. Okay. All right, so when it says write down the rule that connects, this is the given, this is the probability of A given B. A given B. So it's restricting you to the number of people that are in B. So this becomes the number of items in B. Okay. The sample space shrinks from the universal, from U to B. So you're not looking at everybody now, you're just looking at the people or the items that are in B. And then out of those, you're looking at the overlap between A and B. So remember, this stands for number. So when we did it a few minutes ago, the number that were in both was 12. The number that were in B was 40. So here's your rule for conditional probability. Conditional probability of A given B is the probability that of their intersection divided by the probability of B. And then if it's reversed, like this one, you just switch the letters. So this would be the probability of B given A. Now you're only looking at the elements that are in A. Out of the elements that are in A, which ones are also in B? Okay, and then the last one, this would be the probability of A given not B. So now your denominator is the probability of not B. And this is the probability of the intersection of A and not B. Okay, so these are your rules. Okay. And the way that we read these, this is A given not B. That's how I'd read that. I'd read this one, B given A has occurred. And this one would be A given B has occurred. So what conditional probability does, guys, is it shrinks the number of items that you're looking at. All right, now, when we were doing independent events, we learned that this is true. This was the rule that I wrote down earlier about independent events, right here. And we could use that to test if two events were independent. If we multiply these and we calculate what this is, if they're the same, then you can say the two events are independent. All right? So we already have this rule. Now, you can only use this rule if they're independent. All right? So if they're if they're dependent, then we have to have another way of calculating the intersection. All right? So what we're going to do is we're going to take this formula up here and we're going to rearrange it so that this is by itself. The intersection is by itself. So if I take this formula that we got back up here on 5, A given B equals P divided by PB. All right, now what you're going to do is you're going to rearrange this. Okay, so you solve it for P of B. Rearrange for the intersection. A intersect B, which means get it by itself. So what would you do to both sides to get this by itself? Yeah, if you multiply the right side by PB and you multiply the left side by PB, those cancel, and now you have that all by itself. Okay, so a rule for the intersection, the probability of A union or intersect B is P of A times the conditional probability. Or, excuse me, not P of A, P of B. We multiplied both sides by P of B. This side by P of B and that side by P of B. So the left-hand side, this right over here, becomes P of B times the conditional probability. All right, so if you're looking at this, guys, these are two formulas to calculate the intersection. Okay, highlight them or something. Let's see. Okay, this formula gives me the intersection, and this formula gives me the intersection. Okay, you use this one when A and B are independent. So this one's going to find the intersection when A and B are independent of each other, like flipping a coin and rolling a die. This one this guy right here, let's see, so we got that. Okay, this one finds A and B, finds the probability of A intersect B when A and B are dependent. So you've got two formulas to find the intersection. one if they're dependent, and one formula if they're independent. These are your two formulas. All right, then this last part says, what does this imply about the conditional probability and P of A for independent events? Okay, so what this means is the following. If I took this rule, P of B times P of A, B, all right, and then I took this rule, P of A union B, and I'm just going to switch the order of these, it doesn't change anything, P of B times whoops. Okay, P of A. All right. If I told you both of these statements are true, what can you tell me about the probability of A? This top statement's true, and this bottom one's true. What do we know about the relationship between P of A and the probability of A given B? What has to be true about it? Okay. Are these two equal? Yep. Okay. Are these two equal? Yep. They're both P. So then what has to be true about these? Those two are equal. All right. So this gives you a test for independent events. A and B are independent if the probability of A is the same as the conditional probability. Okay. So what this is telling you is P of A is the same as the conditional probability when A and B are independent. This is one way of testing All right, so if these two things are equal, you can say that the two events are independent of each other. So later on in this assignment, you're going to be asked, are these events independent? You're going to use this test to determine yes or no. If these two things are the same, then they're independent. And there's actually two tests. Another test is this. If the probability of the intersection is equal to PA times PB, then if that's true, then A and B are independent. That's another test. So you got two ways of figuring out if something is independent. You could use this and test it, or you can use this and test it. All right, let's try an example here. Can I move this? And I'll scan these guys and put them up on the page. All right. I'm gonna. Okay, so let's do this real quick. I'm gonna move this so it's easier to read. So A union B equals P A times P B. Okay, this right here is also a test for independence. Okay. All right. So you got 84 teachers in the school. Of the teachers 56 drink tea. Okay, so this is, let's see, that's the tea. So these two spaces here add up to 56. Okay, 37 drink coffee. That's this one. All right, and 12 drink neither. So the 12 is outside. So first thing we want to do is we want to figure out how many teachers are in the intersection. How many teachers are there? And we don't know. So we're going to say let that equal X. So we're going to say let X equal the number of people that are in the intersection of tea and coffee. That's this right here. All right, so then what's that make? Only tea. What's this area going to be? If this is X, what's this area? You know, this is 56, and this is 37. 56 minus X is going to be that area. So this is 56 minus X, and over here, this would be 37 minus X. Okay, now figure out what X is. So if I take all of these areas, add them up, it's going to have to equal 84 people. So 56 take away X plus X plus 37 minus X plus 12 has to be 84. Okay, so I got 56 plus 37 plus 12. Okay, 56 plus 37 plus 12. It's 105. And then these x's cancel. So I get negative x plus 105. And then I solve that. 105. You get negative x is 84. Let's see, 105 take away 84. Negative 21. So x is 21. Whoops, sorry about that. Okay, so the number of people that are tea and coffee is 12. or not 12, 21. So guys, the bell's going to ring here in a couple of minutes. So what we'll do is, this part of the assignment will finish on Monday. So for Monday, have 1 through 9 complete.